In this video, I am doing a related rate problem using a production function, the Cobbs-Douglas production function. So take a moment and read the problem. So as always, what we want to do is identify what we know. So down here it says the company plans to maintain a constant workforce of 129 workers. Constant workforce of 129 workers. Well, X is the number of employees or workers. So what does that tell us? It tells us that X is equal to 129. And here's the part that is easy to miss. If we have a constant workforce, that means that the change in employees with respect to time is 0. The other thing that we can see here is the current demand is 997 mass spectrometers per year. So that would be P. That's going to be a P value. P is 997. And to meet the demand, this is increasing by 87 spectrometers per year. So dP dt is equal to 87. So this is what we know. And so that was located right here. And it's while increasing production order to demand, that is increasing by 87 mass spectrometers. So that is a rate of change. What we're looking for here is we want to find how fast should the daily operating budget be increasing? Well, the daily operating budget is Y, which is told to us up here. So what we're looking for is the change in Y with respect to time. That's what we're looking for. So to do this, we need to go to our production function, which is P is equal to 9x to the 0.3 times y to the 0.7. Now there's no way to eliminate the x or the y, as I've done in some other problems. So what we're just going to have to do is we're going to have to take the derivative of this, and we have the two independent variables, x and y. So we're going to have to use the product rule. Yes, we have to use the product rule. And I said independent variables. They're actually both, we have two dependent variables on the right-hand side of the equal sign. So we're using the product rule. So the derivative of P is going to be 1 dP dt. And then I'm going to leave the 9 out here and do the product rule for x and y. So we're going to take x to the 0.3 times the derivative of y, which is going to be 0.7 times y to the, let's see, what's that going to be, negative 0.3 times dy dt plus y to the 0.7 times 0.3 times x to the negative 0.7 dx dt. And let's clean that up a little bit. We have 9. And so what I can do with this and this is I can just kind of combine them. I can say x over y all raised to the 0.3 power times the 0.7 dy dt. And then I can do the same thing over here. I'm going to have y over x to the 0.7 times 0.3 dx dt. Well, the 0.7 times 9, that would be multiplying this times this. Sometimes that's 63, so this would be 6.3 x over y to the 0.3 dy dt. And then 3 times 9 is going to be 2.7 y over x to the 0.7 dx dt. All right, and all of this is equal to dp dt. So there's our big old derivative. Now, in order to solve this we need to solve this for dy dt. We are solving it for this. So we got a little bit of algebra to do here. But first of all, we want to plug in the numbers for dp dt, x and y. Now we know what dp dt is, it's 87. We know what x is, it's 129, but we don't know what y is. So we need to find y. So let's do that. Now to find y, what we're going to do is go back to our original equation, which is p is equal to 9x to the 0.3 y to the 0.7. And we know that p is 997 equals 9. And we know that x is 129 to the 0.3 times y to the 0.7. So solving this for y, we're going to end up with y being equal to 103.7. And so there's our y value. So now it's just a matter of plugging everything into this big old derivative up here. And so that's going to look something like this. dp dt is going to be equal to 87. So plug in the 87. And then we have 6.3. And x is equal to 129 divided by y, which is 103.7. And that's raised to the 0.3 power times dy dt, which is what we're looking for, plus the 2.7. And now we're going to have the 103.7 over the 129, all raised to the 0.7. And dx dt, this is the nice part of this problem, is 0. So since that's 0, the whole second part of this is going to go to 0. So dy dt then, remember we are solving for dy dt. So dy dt is going to be equal to 87 divided by all of this. So that's going to be divided by 6.3 times 129 over 103.7, all raised to the 0.3. And when you do the math on that, if I didn't make any algebra mistakes or any arithmetic mistakes, then that is going to end up being 14.74. Okay. That would be what we are looking for, dy dt. All right. That is the production function problem.